Welcome to today's lecture. I want to look today into the absolute orientation problem. So what is the absolute orientation problem? Why is it relevant? And specifically, how can we solve it? And I want to derive a direct solution from scratch so that you understand how you can compute a similarity transform between sets of 3D points. Okay, so let's start understanding what the absolute orientation problem is about. So consider you have sets of 3D points, in this example 2 sets. So we on the one hand side have the red set called yn and our blue set xn, and these are 2 sets of points. And they should represent the same points in the environment, or the same measured points in the environment, but they are not in the same coordinate system. That means there can be a translation between them, there can be a rotation between them, and there can also be a scale factor between those coordinate systems. So why is this a problem that is relevant? We ever experience this problem whenever we build a local map. For example, we have a camera and move the camera through the environment in order to build the model of the scene, or we have a stereo camera and picture a scene and can construct 3D points of the world. And this is always a setup where I can estimate a set of points, let's say xn in this example, which are points in some local coordinate system, in some camera coordinate system. And often we want to relate that to information we already have, for example, within a map, so in some map coordinate system. And maybe those points are here my points yn. So I know 3D locations in some reference frame, could be a GPS reference frame, could be some other map reference frame. We have those points yn. We want to relate this with new points xn that we're actually generating from our current observations. And in this case, we know some of those correspondencies. So we can see in our image, oh, this is a specific corner. This corner actually corresponds to a corner that I have already in my map, just as an example. And if I have some of those correspondencies, I am actually able to compute the transformation that tells me how the points I estimated in my local frame, where they should be placed in my map or my global reference frame. And that's what this absolute orientation approach is about. Finding this transformation that transforms these points at xn so that the points will overlap with yn. Okay, so let's start. We assume to have a data association or correspondencies. This is shown by these gray lines over here. So I'm saying this point is actually this point, that point here corresponds to this point over there. So these are correspondencies that I know. For example, from feature descriptors. If these are points generated from camera images, I may have used SIFT features or some other form of features to identify points in the world and make this data association, these correspondencies. So for the lecture here today, we assume that these correspondencies are known, they are a given. In the end, we assume we have our known point yn, we have our input points xn, we have the given correspondencies, and what we want to compute is actually a mapping that transforms this point set onto the red point set over here. So a transform of that form, where all the parameters need to be estimated. So what I need to estimate a translation vector t, which basically takes these points and shifts them over here. So this is a translation. Then we have a rotation matrix involved in here, which performs a rotation and rotates those points in some way so that they will overline as best as possible with my red points. And then I have lambda, my scalar value, which can increase the size of the point set, so a scale factor. And especially this scale factor is important when I work with cameras, because quite often I'm actually missing scale information. So if I compute a photogrammetric model, for example, which is a 3D model estimated from camera information, then this photogrammetric model is typically known only up to a scale factor. And therefore, the scale factor matters here if I work with camera data. Okay, so typically those points are not precisely known, they're just approximatively known due to measurement noise and other effects. We never have perfect sensors. So I typically don't find a solution that this point exactly overlaps with this point, and that this point exactly overlaps with the other point. So what I want to do, I want to typically treat this as a minimization problem and find the transformation that minimizes the squared errors between those points. So x bar are here my transformed points. So I say, what's the difference between the transformed points and the final point set? Given that I know my correspondency, so I have n corresponding points over here, this the quadratic error should be minimized. So it's a least squares metric that I want to minimize, or an L2 loss. So where I say, okay, I want to find the transformation so that this function actually becomes as small as possible. So if I have those parameters, if I know lambda, I know r, and I know t, I can actually transform those points and now map the blue points onto the red points. And this is kind of what's called 3D point set registration under a similarity transform, and this is exactly the absolute orientation problem that we want to look into. And again, this is relevant whenever I perform mapping in a sensor reference frame or in a local reference frame, and I want to relate the result, the model that I actually computed, with a map, with an existing 3D model of the environment. Whenever this is the case, then this transformation or this approach here matters. Okay, let's look a little bit more formally what the absolute orientation problem is about. So our goal is to find this similarity transform. So it takes as inputs my points x0 and xn over here and transforms them into a point set referenced here always as x bar n. So every point in xn gets a new coordinate. And this should be done in a way that the squared error between the transformed points and my target points at yn is minimized, and I assume to have no uncorrespondencies. So I basically assume to reorder those points in xn and yn so that x1 corresponds to y1, x2 corresponds to y2, and so on and so forth. So it's important to note that this point set xn could also have, or point set could also have more points. I observe some new feature points, for example, that I haven't seen so far. But those points, if I don't have a corresponding partner in the other set, then they don't matter for computing this transformation. Of course, once I computed these, the parameters of this transformation, I can also transform new points that I've observed in my current camera frame into my existing map. That's clear, but those points where I don't have a corresponding partner in the map, they don't matter for that transformation over here. And again, this matters whenever I have camera data involved. So to align a photogrammetric model with an existing 3D point set that I already have. But this also plays a role when I perform scan matching, want to align LiDAR-based maps. So I have a laser scanner recording 3D points and I want to map them to existing 3D model. This is the so-called ICP, or iterative closest point algorithm, which is typically used in here. And the solution I'm presenting here for the absolute orientation problem is very similar to the direct solution that we use in ICP. The main difference in here is that we have a similarity transform that we are considering, so also the scale parameter, and the scale is typically known for my laser range scanner. So the problem for the LiDAR is actually simpler because I don't need to estimate the scale parameter. I only have a translation and rotation. But in the lecture here today, we treat this as a general problem for the similarity transform. That means we want to estimate also the scale parameter, which I could simply set to 1 if this is the function that I'm minimizing. If I'm working with LiDARs where the scale is known, I of course don't need to estimate that scale. So this is basically a special case of this more general absolute orientation problem. And we can basically see this as anchoring a model in an external map, in an external set of 3D points, in an external model. We are anchoring our locally built model that I built from my local sensor data. And that's what it is all about. So we can, again, use this often when we work with images. So this is basically the notation I used so far in the, for the stereo reconstruction part. So we have a point in our points xn, and I want to transform them with a translation and rotation matrix and my similarity transform. That means I have 7 degrees of freedom, 3 rotation parameters, 3 translation parameters, and 1 scale parameter. And in order to do that, I need so-called control points. So points that I know in my input points, and I know their corresponding partner. These are basically the corresponding points. And of course, I need to know the x, y, z location of the point in the coordinate system yn, how we're using it. Okay, so how does it work? How does it come into the game when I do stereo reconstruction, for example? Okay, so what I have 2 camera images, one taken from here and taken from there, but I don't know the points yet. But what I see, I have my image and I extract feature points, and I can compute corresponding points in both images. These are kind of the 3D points in the world, just illustrated over here. I'm looking with my camera to this point set, but I know those corresponding partners. So from just the correspondence information, I can actually estimate the relative orientation of my camera image, of my stereo pair. Right? So I'm computing, for example, the essential matrix if I have a calibrated camera. And this allows me to estimate where my cameras are with respect to each other. At least 5 degrees of freedom I can identify. So I typically cannot recover the scale, so I don't know how far they are away, but I know where the cameras are looking to and the direction of the baseline vector. That's something I can figure out. So from the correspondences, I can compute the relative orientation. And once I have the relative orientation, I can actually estimate the location of these corresponding points. So far, I only knew they are corresponding. I only have seen them in the images. But now, given the relative orientation, I can actually go back to my image and then compute the 3D location of all the corresponding points in a local reference frame. And this is what we typically call the photogrammetric model. So the photogrammetric model has a 3D location of those points down here, but what we of course are missing is scale information. So we don't know how far those points are apart. We could scale it up or down. And we have no link to an external reference system. So we are missing an external reference frame. So for example, if my camera, I move around in this room, build a local model of whatever the table or the computer in front of me, I still don't know where this computer sits with respect to the door, if the door would define the reference frame for that room. So what I need to do is I need to find a few points, and these are my control points shown over here by those triangles, where I say, okay, this is a point that I see in my image data, and that's a point where I know the XYZ coordinate in the room reference system, so with respect to the door, for example. And once I have that, I know these correspondences. The triangles and the red dots would be my correspondences, and then I would use these 3 points in order to compute this similarity transform. I again need at least 3 points, but I can of course exploit more points. And that's how I would use it, for example, in stereo reconstruction. I can also use this when I'm working with point clouds, so with a LiDAR scanner. So this is an example here, a video by Andreas Nüchter, where you have a robotic platform moving through an underground environment, a mine, and builds 3D point clouds, local 3D point clouds, and lines those 3D point clouds with the data that it has seen so far. And this is done via the point cloud registration using the iterative closest point algorithm. And we have here exactly the same problem of finding the transformation, except that my scale parameter equals to 1, so if an equal scale in the map and in the 3D data, just based on the measuring principle of my LiDAR. So the problem simplifies a bit. I only need to compute a rigid body transformation, but overall it is kind of a special case of the absolute orientation problem. Okay, so again, let's define even more precisely what we have and then try to solve this problem over here. So we have corresponding points yn, xn. xn is my local frame and yn is my target where the xn should be mapped to. And I may have weights as well. So I may have weights for those points. For example, how precisely did I measure them? Or how certain am I about the correspondences, for example. So I have optional weights. I could all set all those weights to 1, which basically tell me what is the weight for that correspondency, how important is it to align these points. And then I want to find the 7 degrees of freedom of a similarity transform, the parameters, my scale parameter, my rotation matrix, and my translation vector with 1 degree of freedom, 3 degrees of freedom, and 3 degrees of freedom. So that we have, this is our similarity transform as we defined it before. And I want to find the similarity transform that minimizes the squared error, or now the weighted squared error between those points. So we compute the discrepancy of the transform point and the target point, compute the squared error, and then weight with the weight factor, and this should be minimized. So this is kind of the final problem definition of the absolute orientation problem, and that's what I want to solve today. So how do we compute those parameters so that this objective is actually met? And what I will provide here is a direct solution. So a solution that where we don't need to iterate, where we can directly with one shot compute the optimal solution under these constraints over here, or for the problem as it is defined over here, I can come up with the optimal solution that I can directly solve. Okay, so from now on, you know what the absolute orientation problem is. Now let's dive into how to compute the solution and how we can actually solve this problem. Okay, so the first thing that I'm doing is I say, okay, I want to work in the local coordinate system defined by the points set yn, where yn serves as my coordinate system for the problem over here. So I've written local here, but it could be your local frame, but this is kind of your target point, your target coordinate system where you want to align all those points to. And we want to define a local coordinate system here, basically saying I'm computing the center of mass of the points yn. The center of mass is yn. I want to do everything related to the center of mass of this point set yn. So what does it mean? I can compute the weighted mean of all the points. This is kind of the weighted center of mass. And then I can simply subtract them from the point set yn and from the point set xn. So I'm basically reducing everything to the center of mass of yn. So in my overall minimization problem, if I expand it, I have my points yn. I subtract the y0. So I'm subtracting the weighted mean. And then this is a transformed point set. So the scale parameter times the rotation matrix times the input point set minus the translation vector. And then also I have kind of the second translation. So if it would be a bracket around here, then this also would be negative of the point set y0. So what I'm basically doing, I'm subtracting y0 and adding y0 here to the minimization problem. So I'm not changing the overall system that we have, so it doesn't change our minimization problem. I'm basically adding a constant and subtracting that constant again, or subtracting the constant and adding it again. And that's what I want to minimize, so this doesn't change my overall problem. Okay? So the first thing that I only did is said, okay, I do everything related to the weighted mean of the point set y0. Okay, now I have that. What I want to now do, I want to kind of rewrite this translational part a little bit over here. So I'm just doing a simple rewriting of the translation vector. So again, we started with this transformation. What we have done on both sides of the equation, we subtracted the point set y0, right? This was kind of because we do everything related to y0. And then I'm just looking to this part of the equation. I actually want to move the translation vector here, which is now my joint translation vector, directly to xn. So as it gets rotated with r, I need to rotate those translation elements by r transpose, so that r times r transpose is the identity matrix, so that I basically find a new translation vector over here, where I kind of first translate the points, then I rotate them, and then I actually scale them. So this expression here, which is underlined in red, I can basically see as a new translation vector where I first perform my translation, then my rotation, and then my scaling. So I take my input points, I first do the translation, then I do the rotation, and then I perform the scaling. So I can now introduce a new variable, and I'm setting this variable, right? So I'm defining a new variable I call x0, could also be any other name, and say this x0 should be r transpose times the translation vector, which is unknown, rotation matrix transpose times y0. So the only thing which is known here is y0, r, and t are unknown for now. So also x0 is an unknown which depends on r and t. And then if I just introduce this new variable, I can rewrite it in this form over here, so that and x bar minus y0 is lambda times r times xn minus this magic newly defined variable x0, right? So if I see it like this, I have changed my unknowns, so I don't have a translation vector t anymore in here. I have x0 in here, but x0 depends on t. So I'm just basically introduced a new variable. And then my unknowns in this case are lambda, r, and x0. Okay? So I've just having done basically a small renaming of variables so far. So I, again, have with this equation, I can rewrite the scale term a little bit and can basically divide both sides by the square root of my scale factor, lambda over here. So lambda to the power of 0.5. If I divide by this term, then I have this equation over here. If I divide by the square root of lambda and I multiply the square root of lambda here, But nothing has changed in this equation except that I have divided by the square root of lambda. And again, my unknown parameters are these lambdas, these r's, and the x0 over here. And I still have the same goal that I want to actually minimize this expression over here. So what I'm doing now is I'm using this form and I'm putting it into my error minimization function to define my objective function. So my objective function phi depends on x0, on lambda, and on r. And I can actually expand this expression over here, and then these are the results that I have. Basically just putting these, the new translation vector, the division with the scale parameter, and the offset, so computing everything with respect to y0 into the equation. And then this is my overall objective function that I want to minimize. Right? So this minimizes the squared error. If I find these parameters which minimize this objective function, then I have the parameters of my similarity transform that I wanted to compute. So the main question is now, how do I actually minimize this function? How do I compute the parameters so that this function gets as small as possible? So the general question, how do I minimize a function? And that's actually not too complicated. We know how we can minimize a function. What we typically do, we compute the first derivative of that function, then we set the first derivative to 0 and solve the remaining equations, and this allows us to compute the minimum of this squared error function, of this squared error. Okay, right, so that's the goal. Computing the first derivatives, setting the first derivatives to 0, and then solving always the remaining equation. And I need to do this with respect to x0, with respect to lambda, and with respect to r, because these are the three unknown parameters that I actually want to determine. So I want to find the x0, the lambda, and the r, so that the function gets as small as possible. I can do this with this approach. Okay, so just to simplify computing the first derivatives, I can basically expand these terms so that I'm expanding basically the dot product over here, and can rewrite this in a form just by explicitly multiplying the dot product. So I get three terms, three sums over here, one sum here on top, which only depends on my scale parameter. All the others are known. I have a second part which depends on my scale parameter and my x0, but doesn't depend on r. And the third part which depends on x0 and on r, but doesn't depend on my scale term. And it's just, you just obtain that by basically multiplying this expression over here. So the important thing to note is there is no dependency of x0 and r in the first row. There is no dependency on r in the second row, and there's no dependency of the scale parameter lambda in the third row. And so this, of course, becomes relevant when I'm computing the partial derivatives, because if I derive this term with respect to whatever x0, for example, I know the first row will be 0, but the other two won't be 0 because there's a dependency on x0. Okay, so let's start working with respect to x0. So we'll now compute the first derivative with respect to x0, set it to 0, and then solve it. And we will repeat the same exercise with lambda and the same exercise with r. As it turns out, it's actually fairly simple to do for x0 and for lambda, but it will get somewhat more complicated for r. And you probably can already guess why, because this rotation matrix R is a rotation matrix which has nonlinear parameters in there, and that gets a bit more complicated, but we are actually able to find a direct solution here, which doesn't work in the general case, but in this special setup that we have here, we can come up with a direct solution. But let's start with x0. Let's solve this with equation with respect to x0, because that's fairly straightforward to do. Okay, so we said we take our objective function and need to compute the derivative with respect to x0. So we take the objective function over here and compute the first derivative. So we need to derive these terms with respect to x0. Again, the first row over here doesn't depend on x0, so this term will go to 0. The second term depends quadratically on x0, and here in the bracket it's a negative sign, so we will have a factor of -2 or of 2 from the outer derivative and the negative sign from the inner derivative. So this basically turns into -2 times the sum, and then only this last expression over here. And for the last row, this is basically a linear dependency because we have x0 only here in this second part of the equation. It's not quadratic as it is here, so the linear term will go to 0. Sorry, will go to 1, and I only have this negative factor, so this -2 would become a +2. Turns out to be a +2, and I have the remaining part sitting over here. So just computing the first derivative of this function with respect to x0. Nothing more than that has happened over here. Okay, so the first part is done of what I need to do. I need to compute the first derivative. First thing done. The second thing is I need to set this first derivative to 0 because I know at the point where I want to minimize, where my function is minimal, the first derivative is 0. So the goal is set this expression here to 0. And that's what I'm doing now. I'm having the first derivative of, or partial derivative of my function phi with respect to x0. I'm setting this to 0. That means 0 must be equal to exactly a copy and paste operation of the term that I had before over here. So that's easy. I'm actually dividing this expression by 2. So these both constant factors go away and move this part to the other side, so it will turn out to be positive. So this simplifies to this expression over here. So this expression over here is this expression, just move to the other side. And this expression is exactly this expression over here. Okay, so how do I minimize this function? What happens actually in here? And so just as a reminder, this x0 is our unknown. Yn is known, y0 is known, r is still unknown. So let's inspect this part over here, which is fully known, because this is the interesting part over here. What's written in here is I sum over all points yn, so, and subtract from it the weighted mean from every point, summing over all points and multiplying it by the weight. So I'm taking a point set, subtracting the mean from the point set, and then basically sum over the whole point set. So that means this expression over here, the whole sum, must be 0, because I'm basically computing the mean and before subtracting the mean from that point set already. So I know that the result must be 0. So this equals to 0 as y0 is already the weighted mean of x0. Okay? So this term is 0. If this term is 0, it's just 0 multiplied with a rotation matrix, so I know this whole part must be 0, and as a result of this term also must be equal to 0. So as a result of this term here must be equal to 0. Okay, so I can move this to the other side, and this must be 0, and I know my scale factor is unequal to 0. I can basically divide by lambda over here and obtain this expression, and if I just bring x0 to the other side, this is my final result. So as it turns out, the x0, and that's the reason why I gave it the name x0, is also the weighted mean of the point set x, of the point set xn. But this is actually a coincidence. This is something which happens based on the result over here. So x0 is the weighted mean of the point set x0. This was nothing which I exploited before. I just introduced a new variable in the beginning, but this variable turns out to be the weighted mean of all the points x0. And so, of all the point xn, sorry. So x0 is the weighted mean of the point set xn. And this is the optimal value for minimizing our objective function. Okay, so the first thing we know, x0 now is fully known, which x0 minimizes the overall expression that we have. Okay, so let's do the second exercise and look what happens with the scale parameter. So next thing we do is we say, okay, how does this scale parameter look like? We need to solve our expression with respect to lambda. So we take our objective function, we derive it with respect to lambda, we set it to 0, and then we solve the remaining equation. Okay, so again, copy-paste our objective function. And again, lambda only appears in the first two rows. The second row is independent of lambda and completely vanishes. So my objective function derived with respect to lambda. I see here this is 1 divided by lambda. This term sits over here. So this becomes -1 times lambda to the power of -2, which I have over here. The rest remains the same. And here, this is a linear term. If I derive the linear term lambda simply goes away and a constant remains, so only the remaining part of this equation here still remains. So this is my first derivative, and what I now need to do, again, I take this term and set this term to 0. So d phi with respect to d lambda should be equal to 0. That means this term must be 0. And that's now a very trivial thing to solve with respect to lambda. So I'm just adding this term to both sides of the equation. So it goes away on the right-hand side and moves to the left-hand side. Then I have lambda to the power of minus 2 sitting over there times a constant equals something else. So I just divide the remaining expression by this term over here. And then I, of course, this is 1 divided by lambda square. I kind of flip that and compute the square root so that I will have this expression here remaining. So we directly get the solution for lambda over here. And again, my scale factor is supposed to be positive because it just tells me the size of my problem. It should be larger, actually larger than 0 over here. So this is the remaining expression, which tells me how the scale factor needs to be set. And it only involves terms that I already know. It involves my y zeros, y n's, which I know xn is known, and x0 is something that I just computed beforehand. Again, something which is by now completely known. So I can directly compute my scale factor, and then this is a scale factor which minimizes the squared error between my transformed point set and my target point set. Okay, again, that was fairly simple. I just need to compute the first derivative, set it to 0, and then solve a fairly simple equation. And this brings us now to the last part, which means solving this with respect to the rotation matrix. And that's a part which gets a little bit more kind of non-standard and a little bit more complex, and the reason is because this is a rotation matrix over here. Okay, but let's start exactly with the same principle. We are computing the first derivative of this function, and then want to set the first derivative to 0. Okay, so I again look into my objective function, and now I can again look to my first row of my objective function. See, actually, there's no rotation matrix popping up here at all. Also, the second row over here, no rotation matrix is popping up. That means only this term, the last row, is the one which matters because it's the only term where the rotation matrix pops up. So I can ignore those two and only need to take care of that second part because everything else is known. I only need to determine the rotation matrix, and the rotation matrix only impacts the term down here. So this is a negative term. So instead of, when I want to minimize this function, I need to maximize this expression without the negative sign over here. And then I can also ignore the 2, my constant factor. So what I need to do is I need to maximize this expression over here. So if I'm maximizing this expression over here, the overall objective function gets as small as possible. So I need to find R star, my optimal rotation matrix, by looking over all rotation matrix so that this term gets as small as possible. And I have the constraint here that R transpose R must be the identity matrix, the property that we have for our rotation matrix that must hold. So this is the task that I now need to solve. And that's, again, somewhat more complicated. And we will now dive into the details on how we can actually solve this problem. And what I actually will show is I will actually present a solution on how we set R, and then actually show that this is the optimal choice for R that actually maximizes this expression over here. Okay, so let's start. And the first thing we do is we just do, we call something we call reduced coordinates. So I'm just replacing my my yn and xn with variable a_n and bn. And a_n is just the points in my original point set minus the weighted mean of that point set, and bn is the same for the target point set. So I'm basically taking my input point set and my target point set. I'm just subtracting the mean, the center of mass of these points. So both point sets have the same center of mass, which is 0 for those reduced coordinates. So basically, it's just something that I can actually realize with a simple translation. And I'm now working with these a's and b's. The mass gets more compact over here. So what I'm doing, I'm replacing this term here by bn and this term here by an, so that the objective function that I need to maximize now is exactly this expression over here. So bn transposed r times an times my weight should be maximized. So I need to find r so that this term gets as large as possible. That's kind of the task that I need to do. Okay, so what I now do, I use now the definition of the trace to rewrite this term a bit and come up with a new matrix H, which is the cross-covariance matrix of the point set that I have. Okay, so how does it look like? So this is what I'm starting with, just copy-paste what I had before. And I can actually replace this expression over here by the trace of this rotation matrix R and a matrix H, which is the cross-covariance matrix computed over the reduced coordinates A and B. So basically, this product with B transposed and A, I use this to form a cross-covariance matrix. Then I rotate this matrix as a rotation matrix R, compute the trace, and this exactly gives me the sum of the diagonal elements. So it's just kind of using the trace to rewrite this form over here. So this is a complete equality over here. So I can rewrite this expression in a form that I have the trace of a rotation matrix and my matrix H, and my matrix H I can directly compute from my reduced point set. So again, H can be directly computed because I know y, I know the yn, I y0, I know xn, I know x0. So this is something that I can directly compute, this matrix H. There's no unknown in there. And then I know, okay, I want to maximize an expression where I say the trace of a rotation matrix times this completely fully known matrix H. This should be maximized, and this is then my optimal rotation matrix. So I need to find R that maximizes the trace of R times H. This is now the goal that I have. And by now I've just kind of rewritten my expression a bit. I introduced this reduced coordinates and used this trace here for rewriting the expression. So far, nothing very fancy has happened. And the next thing comes to the game, what happens right now. What I'm doing next is I'm exploiting the singular value decomposition, or SVD. Again, SVD, used it a few times already in all my courses here. It's a technique that I use in order to decompose a matrix H. So the SVD of H can be broken up into three matrices, a matrix U, a matrix V, and a matrix D. So that U times D times V transposed gives me my original matrix H, where UV are rotation matrices and D is diagonal matrix containing all the singular values of my matrix H on the main diagonal, and V contains the singular vectors corresponding to the individual singular values. And what we're doing for now is we're just kind of using this decomposition. So we're just decomposing this matrix H into three matrices. And because we are basically interested in this matrix U and this matrix V transposed, and what we're now doing, we are just defining a rotation matrix. This is kind of where the magic comes into the game, which is kind of what we're doing is I'm providing basically a solution, then tell you that this solution, or prove that this solution is the optimal solution. So what we're doing is now we're using this matrix U and this matrix V defining my rotation matrix. And this, again, may sound not obvious at the moment because you don't know why I'm actually doing this. But I'm doing this and okay, accept this for the moment. I'm proposing you an R on how to build it, and then I will later on show you that that's actually the best R you can do. So you should be fine with it. It's hard to derive it by yourself or to come up why this is the optimal R, but you can actually show later on that this is the optimal solution. Okay, so I tell you now that you should define your R, your rotation matrix, as V times U transposed. And if we do this, then I will actually show that this expression over here gets maximized, and that's what I want to do. Okay, so let's simply see what happens if we set R, give R exactly this shape over here. So we have the trace of R times H. So this is the trace of, now I'm replacing R with this expression over here, V times U transposed. And H is nothing else than U times D times V transposed, just the definition of the singular value decomposition. Okay, so I have here a matrix U transpose times U rotation matrix, so I know that this is an identity because a rotation matrix transpose times the rotation matrix gives me the identity. Okay, so I can rewrite this as a trace of V times D times V transposed. Nothing bad has happened so far. The next thing I'm doing, I'm exploiting this constraint that this matrix D is a diagonal matrix. That means it's zero everywhere and just has non-zero values on the main diagonal. Maybe there are even some values which are zero if the matrix has singular values which are zero, but it will turn out later on that's bad for my point set because I actually have a degenerated solution. So typically all the values on the main diagonal, so the singular values are non-zero or larger than zero for this D. So if I have a diagonal matrix, I can actually compute a second matrix, which I now call square root of D, which is just the same matrix D, except that I compute the square root of the singular values and put them on the main diagonal. So that if I multiply square root of D times square root of D, I actually get my original matrix D. So I can very easily define square root of D by just take the diagonal elements and just compute the square root. So making a small square root sign over all the elements on the main diagonal. The rest is anyhow zero, I don't care about that. If I do this, then I can actually break up this matrix D into saying, okay, this is nothing else than square root of D times square root of D. This gives me D again. And I can do this because I know from the singular value decomposition that all the diagonal elements are actually positive or larger or equal than zero. Okay, so that's what I have. I have now broken up my trace of R times H into the trace of V square root D V transposed. Okay, let's start from this. Just copy paste from the previous slide. What I can now do is I can move this square root of D into the transpose sign. This only works because this is a diagonal matrix. It wouldn't hold if it would be a general matrix, but given that square root of D is a diagonal matrix, I can move it inside the transposition. And then, this is my final result that I have. So I have actually a sequence. I can treat this as one single matrix, and this as a one single matrix, where the one is the transposed of the other. So I can define a new matrix H as V times square root of D, so that this expression simplifies to A times A transposed. So the key thing in here is I was able to rewrite the trace of R times H to A times A transposed if and only if I set R in the way I set it. Because I told you how R should look like, and if you set R as I told you, this equality will actually hold. And we can also show that, and I'm not going to the details right now, that A is a positive definite matrix. This becomes important in a second. You can go to Arun if you want to know into the details, but at least if the transformation that I'm actually having is something which occurs typically, so I have rotation, translation, and a regular scaling, then this is actually the case. This is always a positive definite matrix. If I have a reflection, for example, of my points in my transformation, then this would not be the case anymore. But this is something we don't have in our regular point set that we observe if we observe points in the 3D world. So A is a positive definite matrix that we have over here. Okay, so we know that this holds and A is positive definite. And what I then can do, I can exploit the Schwartz inequality, which basically says me for every positive definite matrix A holds that A times A, the trace of A times A transpose is larger or equal than the trace of any arbitrary rotation matrix R prime multiplied with this term over here. So I can take any rotation matrix, multiply it with A transposed, and compute the trace, and this term will always be smaller or equal than my original term. That's what the Schwartz inequality actually tells me. Okay, if this is the case, this is something that I can exploit, because then I say, okay, my trace of R times H equals to trace of A transposed, and this only holds given my definition of R. And I can show this is larger or equal than any rotation matrix R times this expression over here. And now I can say, okay, this was nothing else than my R, so A transpose was nothing else than R times H, right? So I can treat this as R prime R times H. So I have two rotation matrices sitting over here. Product of two rotation matrices is again a rotation matrix. And I know whatever rotation matrix R prime I multiply to my rotation matrix R will lead to something which is smaller or equal than what I had before. So there's no rotation matrix that is better than my rotation matrix R, because everything else will lead to smaller traces, to smaller values. So my choice of R, saying this is V times U transposed, was the best choice I could do, because everything else will lead to a smaller trace. This means I've maximized my trace expression, and in this way, my objective function. So exploiting the Schwartz inequality allows me to say my definition of the rotation matrix R was the optimal choice. So again, there's also if you want to understand why this is the case, the proof for the Schwartz inequality, just copy paste it in here. If you really want to dive into the details and understand why this is actually the case, but for now, for here, we just assume it to be correct and given. Okay, so that means the optimal choice for my rotation matrix R is V times U transposed, where V and U are the two matrices which stem from my singular value decomposition, which I computed over the cross-covariance matrix of my reduced coordinates. So I need to compute my matrix H by just saying, okay, I take my point set containing all the x's and all the y's, and I'm just subtracting the weighted mean from all the points, and I compute the cross-covariance matrix out of that. This is my matrix H. Then I compute the singular value decomposition of H. This gives me these three matrices, and I just take U and V out of this to define my optimal rotation matrix R. And with this, I computed my translation vector, or my vector x0 to be more precise, but which is directly related to the translation vector. I computed my scale parameter, and I computed my rotation matrix. So all the parameters of my objective function phi in order to minimize it. A short remark on the SVD solution that I just computed. The question is this a unique solution? Given that we are here in the setup that we have that U and V are both 3 by 3 matrices, because we have 3D points over here, and D has the diagonal elements, if H is of full rank, that means the singular values that we have in here are all larger than 0, so there's no 0 diagonal element in D, then it is actually a unique solution that we get. Again, we can end up in situations where so I need to check that R times H that I'm computing is a positive definite matrix, otherwise the Schwartz inequality wouldn't hold. But again, typically it's negative only if I have a deflection of points. And typically these deflections is something that doesn't appear in real-world situations where you have point sets observed from a laser range scanner or from a camera system. So that's something that doesn't really happen in the real world over here. So it's actually a unique solution for most realistic problems. So the last thing we need to do is we need to compute actually our rotation vector t, because we only determined x0, but there was a direct relationship. So if you go back, x0, this was the definition of x0, where all terms are known except of t, so I just expand this to t. So t is nothing else than the weighted mean of my target point set minus the rotation matrix that I just computed and the weighted mean of my source point set, so something which I can directly compute. So with this, I get all the 3 parameters of my original transformation that I want to compute. In order to turn the input point set xn, my blue points in my initial example, into the red point set, so target point set. And the only thing I need to do is I need to compute the weighted mean of my input point set, the weighted mean of, a weighted mean of my input point set and weighted mean of my target point set. I need to compute this cross-covariance matrix H based exploiting x0 and y0. Then I compute the singular value decomposition I take the matrix U and the matrix V out to define my rotation matrix. I can directly compute my scale parameter, and I can directly compute my translation vector. And then I have all parameters that I need in order to minimize my objective function. So coming up with the optimal solution of the point sets, taking into account that every correspondency can have a single scalar as a weight factor. And that's it. I solved the absolute orientation problem to find the optimal translation parameters, or transformation parameters, not just translation parameters. Scale, rotation, and translation. If you look that up in a book, you be aware that you may find two different variants of this, but they are equivalent. So what I can do is I can swap the way I define my matrix H. So I'm reducing the using the reduced coordinates of x, y, or yx in the opposite direction. So I can swap this. If I swap that, then I also need to swap the elements here of the singular value, the matrix V and the matrix U. So just to be aware, if you find a different definition on how to compute R, then the reason is that the matrix H was differently defined, but it's completely equivalent. By just replacing the A's and B's and defining A's and B's in a different way, then you will get the other rotation matrix defined, and you will have come up with the same solution. So just as a side note, there's a different way how you can actually write it down, but it's just you're just basically swapping two variables in the beginning, and that means that you also need to swap them in your rotation matrix, because then the one rotation matrix is simply the transpose of the rotation matrix of the other rotation matrix. Okay, this brings me to the end. What I presented you today is a solution to the absolute orientation problem. The absolute orientation problem was the problem of finding a similarity transform between two point sets given known correspondencies, and finding the transformation parameters of this similarity transform so that minimizing the weighted squared error of the transform point and my target point set. And that's something, a technique that we frequently use if we want to align maps with each other. So let's say we have a map that we computed with one sensor and a map reference frame to which we want to add that new data. Then this is one way based on some points that I know in both point sets. Through those correspondencies, I can actually compute these similarity transform parameters. And we especially use it in photogrammetry in order to align a local model that we have, a photogrammetric model, which is defined only up to exactly those 7 degrees of freedom, and align them with an existing map which already has a scale parameter, for example. Or we can use it for when we work with lidars, although then we don't have a similarity transform, then we only have a rigid body transform. So we basically drop this scale parameter lambda that we have, just lambda goes away, and the rest of the solution stays the same. So the basically ICP-based direct solution for the point cloud alignment is a special case of this absolute orientation problem over here. Again, it's efficient to implement, and it's a very effective and popular approach that is used very frequently. Is one of the techniques you should know if you want to combine 3D data from different sources with each other. With this, I say thank you very much for your attention and hope you understood, or were at least able to follow and understand how we come up with this solution for the absolute orientation problem. So even if you just apply this in the future in order to align point sets, because then you just will basically ignore everything I told you in the last 30 minutes, just the first 15 minutes mattered, and you compute your H matrix, do the SVD, define your rotation matrix, and you say, I'm happy with it, that's also fine. But at least you can go back and say, okay, that's the way how it worked, and the take-home message is, it's actually no black magic which happens in there. The only thing we did is we defined an objective function, we computed the first derivative, set it to 0, solve it, and the only trick that we needed to do was for this rotation matrix where we basically exploited in the Schwartz inequality in order to say how does this rotation matrix, how does it need to look like so that it's actually better than anything else, any other rotation matrix we can set. With this, thank you very much for your attention.